So in our previous discussion, we specifically required that omega naught and omega could not be equal to each other. Let's consider now, what if they are equal to each other? Well, the big problem from a mathematical point of view is that our previous particular solution doesn't work anymore. In fact, if you look back to the section on undetermined coefficients and look at the procedure by which we should expect to find the form of our particular solution, everything is in fact different. So let's go back a couple of pages. Here's our differential equation. Looking at the right-hand side, the number that we, in section 4.3, called a plus bi, would be omega I. And the thing about it is that omega I is a root of the characteristic polynomial that you get from looking at the left-hand side. So you have to stick in, as a result of that, an extra factor in the form of your guess. That's an extra factor of t because the independent variable here is t. So we have to stick in an extra factor of t, and this won't work anymore. There needs to be an extra factor of t in the sine and cosine terms that go into the form of this guess. Working out the details, the particular solution turns into this. There's that extra factor of t. Okay. Because omega I is a root of the characteristic polynomial. Thus that. Okay, now there's a bunch of algebra to check here, and students should do this. Students should write down what the form of the particular solution would be and go through and solve for the coefficients. It's not that bad. It's a good exercise. Make sure that you can do that, and then this is the answer that you should come up with. Okay, so now that we know that particular solution, let's ask, what does this look like? Well, and of course there's homogeneous solutions as well. But notice, again, you can interpret this as an oscillation. There's an oscillation. And then there's this amplitude, but this time this is not a decaying amplitude, and it's not an oscillating amplitude. This is an amplitude that simply grows with time. It just keeps getting bigger and bigger, and you just expect that these solutions would keep doing this growing. Just getting bigger and bigger and bigger and bigger. Okay, now don't forget what we're talking about here. Our model that we're considering is that we have a ceiling joist and a spring, at the end of which is a ball. And according to this solution of this differential equation, what we expect to happen in this case, where the external forces are controlled at a frequency that's equal to the natural frequency, then what we would expect is for the oscillation to get more and more and more, and something's got to give at some point. Well, so what this means is at some point the differential equation breaks down. At some point the differential equation ceases to be a good model. In this particular case, for example, eventually the ball hits the ceiling joist. Well, then there's all sorts of new forces that are introduced, and the differential equation really should change. And since we're only looking at the same differential equation, the better way to say that is that the model breaks. The model is simply no longer representative of reality at that point. Okay. Now, one interesting thing about these differential equations, so here's our differential equation that we've been considering, is that these are just models. And this external forcing term here is just an example of an external forcing term. And of course there's lots of different actual external forcing functions that we could talk about. And there's lots of things that maybe aren't exactly springs, but nevertheless behave somewhat like springs. So there are a lot of situations that, even though they are not technically exactly a mass on a spring, they are still nevertheless reasonably well modeled by a differential equation, kind of like this. So one that you could argue is not unlike this is a bridge. So we don't exactly have a mass on a spring, but the bridge nevertheless has a certain amount of a mass. It's not exactly on a spring, but the structure of the bridge, if you push it one way, there will be a tendency for the bridge to push back the other way. And we might not be applying exactly sinusoidal forces to it, but we might be applying periodic forces to it. So in fact, this is a reasonably good model. Not exactly, of course, but this is qualitatively at least, a reasonably good model for the behavior of a bridge when there is some sort of a periodic force applied to it. Well, gosh, I sure hope that this is not describing the behavior of the bridge while we're standing on it, right? This is scary. If the motion of the bridge gets more and more and more, well, eventually, instead of the cannonball hitting the ceiling joist, maybe the bridge just moves enough that the bridge breaks, right? That's a definite concern. So this is a very dangerous phenomenon, this phenomenon of resonance. So, in other words, if there is an external force, some sort of external force that's being applied to your situation, you have to make sure that the natural frequency of your system, whatever that is, can't equal to that. Because if it does, then you sort of expect something catastrophic might happen. So there's some examples, and we'll talk about these in class. The London Millennium Bridge you can read about. There's also some discussion of the Tacoma Narrows Bridge. This actually is not a good example. We'll talk about the details in class.